Let's move on to what happens if we start taking roots of complex numbers. Okay, so we're happy with taking powers of complex numbers. Let's see what happens if we start taking roots. So we start finding the square root or the cube root. So this idea of taking roots of complex numbers extends from this. In fact, this is what we're going to reuse again. We're just going to make a slight tweak to the formula, slight tweak to it. So here is the idea. Let me start off with a slight thought experiment. If I ask you to solve this equation here, how many solutions are there to that equation? Do we remember the fundamental theorem of algebra which says you look at the highest power of the polynomial and that tells you how many roots there are, that tells you how many solutions there are. So here the highest power is 1, which means that there should be one solution. Okay? So what is the solution of this equation? Good, it's x equals 1. What I'm literally saying here is I'm taking some number, I am raising it to the power of 1, and it equals 1. What is that number? It's just 1. 1 to the power of 1 equals 1. Okay? Now if I plot that on the complex plane, this is where it is. Okay? It's just a number at 1. So x to the power of 1 equals 1. What I've literally done here, if you like, is I've taken the first root of 1. Of course, we'd never write it like that, but you get the idea. Okay, so we've taken the first root of 1, and we get one solution here. So let's extend the idea then. Let's see what happens if I try and solve an equation like this. So x squared equals 1 now. Now, how many solutions am I expecting? 2, because that 2's there. Okay, so how am I going to solve this? Well, I take the square root. Okay, so I take the square root of 1. Of course, taking the square root of 1 is a little bit dodgy, but we'll stick with it at the moment because there should only be one solution here, but you get the idea, okay? Right, so what are the solutions? There's 2 solutions to x squared equals 1.
Plus minus 1.
Yeah, exactly. So you get x equals 1 or x equals negative 1 as well. So if we plot that on the complex plane, so we raise it to the power of 2 now, that's what we get. Okay, so there's a solution over here, this one here, but there's also a solution over here in the exact opposite direction. So okay, let's keep going then. What happens if I want to solve something like this? How many solutions are we expecting? We're expecting 3, right? Because the highest power is 3. You get the idea. Okay. So how are we going to solve this? So we take the cube root of x. So we take the cube root of 1, right? Like here we took the first root of 1, here we take the second root of 1, here we're taking the cube root of 1. Okay, what I'm trying to do here is link this idea that if you're trying to solve an equation like this, what you are literally doing is finding the roots. Okay? Can somebody tell me what is the cube root of 1? Like if I want to solve this equation, I'm looking for 3 roots. Can anybody tell me a solution to this equation? I mean, there's an easy one, there's an obvious one. A number times itself 3 times gives me 1. Can you give me an answer? 1, right? That's the easy one. What about the other 2? Like we're expecting 2 more, we're expecting 3. So where are the other 2? Okay, so you're starting to suspect that it's probably going to go into the imaginary numbers, hence we're looking at in complex numbers, okay? So you are right. Like if you only knew about real numbers, and you're saying, the fundamental theorem of algebra tells me that the highest power is that many roots, so that's how many solutions there are to the equation. So I'm looking for 3 solutions, but only using real numbers, I can only find 1. Like negative 1 won't work because that will give me negative 1 cubed makes negative 1. That's no good. So where are the other 2? They're hiding in the complex number plane. So here we go. Raise it to the power of 3. There they are. Okay, so there's 1 here, that's the one which we found, that was the easy one, but there's also 1 here and 1 here. There's 2 which exist in the imaginary numbers. Okay, so it is like the r equal to 1. Good, so the radius is still equal to 1. Radius is still equal to 1, but what is the argument, I wonder? So the argument is the angle which we've moved through. So effectively what we get is something like this. So we get one of our solutions out here at 1. Okay, that's one of the solutions. But then we get another solution out here, and we get another solution out here. Now, in order to understand this in a little bit more detail, let's trace our minds back to this one. So with x to the power of 1 equals 1, we found that there was a solution over here. We found there was a solution here at x equals 1. Okay? With x squared equals 1, there were two solutions. So that's real and that's imaginary. There was a solution over here at positive 1, but there was also a solution over here at negative 1 as well. Okay? So I wonder if you can notice the pattern. So we go from here to here to here. Let's think about what would happen with x to the power 4 then. So we took x to the power 4 equals 1. Again, we're looking for 4 solutions, so effectively we're solving an equation like this, taking the 4th root of 1. Okay? Well, there's 2 solutions which you can tell me. Yeah, exactly. There's 2 solutions which you can tell me. One at 1, like 1 to the power 4 equals 1. Also one at negative 1, right? But where are the other 2? So, or x equals, where are the other 2? Well, they exist in the complex plane, okay? So Sky, you're dead right. You can kind of figure out what's going to happen here. You've got real here. You've got imaginary here. There's 1 at 1. There's 1 over here at negative 1. But there's also 2 more. There's 1 there and 1 there. In fact, if we look at that, we can see that quite nicely. There's 1 there, 1 there, 1 there, and 1 there. So what are you starting to notice about this? What do you notice about the roots of these numbers? Where do they position themselves in relation to the angle or the argument?
So it's just like 2 pi or the power?
Absolutely, yeah. So you look at this, you say, right, it's 2 pi divided by the power because all of these complex numbers are equally spaced. That's one of the nice things about it. I think this is quite cool. Right? So all of the complex numbers, all the roots, will be equally spaced apart. So have a look. That one, there's only 1 of them. It's equally spaced. It's just a full term. It's just 2 pi. So if you like, the spacing between them, if I create a 3rd column over here, which corresponds to spacing, the spacing between this one is just 2 pi divided by 1. Okay? The spacing between these two is just 180 degrees, or pi radians, which will just be 2 pi divided by 2. Is that okay? Yeah? And the spacing between these ones will be, okay, so it's 2 pi divided by 3, because there's 3 spaces between them, if you like. So it'd be 2 pi divided by 3. Okay, that's the spacing between them. Okay? Spacing between these ones will be 2 pi divided by 4, or pi by 2. In other words, they're spaced at 90 degrees apart. Is that okay? So if you want to find the root of a complex number, like, you've just got to think all of the complex numbers are equally spaced apart. Is that okay? So now we can come back and answer this question then. So, well, actually, let's do this one first because it's easier, right? We found one of the roots. We found another of the roots, 1 and negative 1. We found the real ones. Where are the 2 complex roots? Yeah, good. I and negative I. Because they've got to be 90 degrees apart, or pi by 2 radians apart. So x equals I, or x equals negative I. Okay? Now if we come back to this one, we found this root was at x equals 1. The other 2 roots will be up here and down here. So how far apart are they? They're 2 pi by 3 radians. So what are the other 2 roots? Okay, so we know that the modulus is 1, so we can write this in polar form. So let's call this one Z1.
Argument is different.
Yes, exactly, and this is my point. The argument is worked out because the spacing between the numbers is 2 pi by 3 in this case. So Z2 will have a radius or a modulus of 1. And then the argument, well, are you happy that we've moved from the positive real axis, that's the first root, and we've moved through an angle of 2 pi by 3? Do you see that? Yeah, because you said that the spacing between the numbers is 2 pi by 3, so the space between this one and this one must be 2 pi by 3. So we've gone cos of 2 pi by 3 plus I sine of 2 pi by 3. That's my argument. That's my second complex root. Is that okay? So keep going then. Could you tell me what this complex number is? So let's keep going for another 2 pi by 3. So you're happy the modulus is still 1. What's my argument? That's the tricky bit.
4 pi by 6.
Yeah, good. I've gone, oh, careful. 4 pi by 3, isn't it? 2 pi by 3 times by 2. Yeah, so 4 pi by 3. Good, we can add fractions. Plus I sine of 4 pi by 3. Are you happy with that? Yeah, so actually I don't need the ones there. So my two other complex numbers are cos of pi by 3 plus I sine of, 2 pi by 3, or x equals cos of 4 pi by 3 plus I sine of 4 pi by 3. Is that okay, like just from an intuitive perspective? The spacing between the numbers is worked out by this. You just simply take 2 pi and you divide by whatever power you're raising your equation to. And then in this case, the radius, we're not worried about that, it's just 1, because we're solving roots of unity. Okay, it's just 1. Okay. Now, in fact, if you want to see the nice, pretty drawing going, so I can do this quite nicely. There you go. So raising it to higher and higher powers. Okay, it's quite a nice, pretty thing. Okay, what I'm trying to show you here is that the spacing between the numbers is always the same, and the spacing corresponds to whatever power you're raising it up to. Okay, so it's just 2 pi, which is a full turn, and then you're dividing it, you're splitting it equally amongst whatever power you're raising it up to. So if you're raising it to the power of 10, I can pause that. If you're raising it to the power of 10, like that, then the space, there's 10 spaces between the numbers, so it'll be 2 pi divided by 10, or pi by 5.